torque on an electric dipole in an external electric field. This is a uniform electric field. Okay. If electric field is represented by equidistant and parallel lines, then this electric field is uniform. Let us keep a dipole. Dipole is two equal and opposite charges separated by small distance, something like this. Okay. We know that plus Q experiences force in the direction of the electric field, like this, and minus Q opposite to the direction of electric field, because force is given by Q into E. Force on positive charge means plus Q into E is F. So in this case, direction of electric field is the direction of force. That is this. Now, on a negative charge, force is minus Q into E. Minus QE means the direction of force is against the direction of field, something like this. So negative charge against the field, force on positive charge is in the direction of the field. Now these two equal and opposite forces constitutes a couple, and moment of the couple is nothing but torque, denoted by tau. Moment of a couple means turning tendency of two equal and opposite forces. Moment of a force means turning tendency of a force, that is also called torque. Turning tendency of a force, this is turning tendency of equal and opposite forces, that is couple. Okay. Consider an electric dipole in an external electric field E. The dipole moment is given by P equal to Q into 2A into P cap, where Q is magnitude of each charge, 2A distance between the charges, P cap unit vector. P cap is unit vector from minus Q to plus Q along the line joining the charges. Let theta be the angle between P and E. Uniform electric field is represented by equidistant parallel lines. This represents uniform electric field E. Let this be a dipole. This is minus Q and this is plus Q. Plus Q experiences force in the direction of the field. So this is the direction of force on Q, and this force is Q into E. Direction of force on minus Q is against the electric field. So this is the force on minus Q. Make sure that length of this is equal to length of this, means these two forces are equal and opposite, not acting on the same line. QE, because I am just writing the magnitude. To find out torque, shortest distance between these two forces matters. Okay. Before that, let me write P cap. The direction of dipole moment is from minus q to plus q along the line joining the charges. So this is the direction of P cap. This is electric field. So angle between P cap and electric field is theta. Now, to find shortest distance between these two forces, observe this force is represented by this pen. This force is represented by this pen. Shortest distance between these two means it is this perpendicular distance from here till here. Okay. Perpendicular. One more perpendicular. If this point is A, this is B, and this is C, AB is the shortest distance between these two forces. Force on plus Q in electric field E is F due to positive charge equal to Q into E. The direction of this force is along E. Force on minus Q in electric field E is force due to minus charge Q into E against E. These two equal and opposite forces constitutes a couple. Therefore, torque is tau. Moment of the couple. Moment of the couple is force into perpendicular distance. Magnitude of each force is Q into E. Shortest distance between the forces is AB. So, force into perpendicular distance. F into AB equal to F. Shortest distance is AB, which is equal to F is Q into E. AB is observe, if this is theta, this is theta, alternating angles. AC is 2A. Distance between the charges is 2A. Therefore, this is opposite side for this theta. Opposite side hypotenuse means sin theta. So AB is AC sin theta. AC sin theta equal to Q into E. Q into E. AC is 2A into sin theta. This is torque. Q into 2A is nothing but P. Magnitude of P. E sin theta. Torque is a vector quantity. Dipole moment is also a vector quantity. Electric field is vector quantity. Therefore, in vector notation, we can write tau equal to P cross E. This is the expression for torque on an electric dipole in an external electric field. Since it is cross product of P and E, the direction of tau is perpendicular to both E and P and E, following right hand screw rule that we have to mention. The direction of tau is perpendicular to both vector P and vector E, following the right hand screw rule. Now simplest way of finding direction of tau, make sure that curvature of right hand four fingers is from P to E. Observe the diagram. The direction of P is this. Let me keep my fingers in the direction of P. I should bend the fingers towards E. I cannot bend like this. I can, but this is not the way to bend, right? So change the direction. Now bend it. Curvature of finger should be in the direction of E. Open the thumb. Thumb will be pointing downward. Means direction of tau is perpendicular and into the plane. Therefore, in this diagram, we can write direction of tau is perpendicular and into is represented by this symbol. Let us make it tau cap unit vector. Now special cases. First one, if theta 0 degree, since cross product has sine theta, what matters is sine. Sine 0 is 0. Therefore, tau is also equal to 0. What is the meaning of tau equal to 0 if theta is 0? This is uniform electric field and here is a dipole minus Q plus Q. This is electric field. Force on plus Q is towards E. Force on minus Q is against. These two are pulling the dipole apart. There is no rotation. That is the meaning of tau equal to 0. Resultant force is 0 and torque is also 0. This is for your reference. Tau is 0, nothing but torque is 0, and resultant force, Fr stands for resultant, is also equal to 0. Second note, if theta is 90 degree, if theta is 90, sine 90 is 1, then torque equal to P into E, and this torque is maximum if theta is 90 degree. Torque is maximum. This is electric field. This is the dipole minus Q plus Q. Dipole moment is from minus Q to plus Q. So this is P cap. This P cap is perpendicular to E. And force on plus Q is in the direction of electric field, minus Q against. For this configuration, turning tendency of these two forces is maximum. That is the meaning torque is maximum if theta is 90. Now third case, if theta is 180, then sine 180 equal to 0. If sine 180 is 0 means again torque equal to 0. Electric field. Now we should make theta 180. Let this be the dipole. Now this is minus Q and this is plus Q. As you can see, plus Q is towards E. Direction of dipole moment is from minus to plus. So this is P cap. This P cap is parallel to E. Of course, P cap is in the direction of E. For that reason, theta is 0. In this case, this is the direction of dipole moment, P cap. This P cap is against E, external electric field. So in this case, force on plus Q is in the direction of electric field, minus Q is against the direction of electric field. Resultant force is 0. Let me write Fr equal to 0. Tau is also equal to 0. So this configuration is said to be in unstable equilibrium, whereas this configuration is in stable equilibrium. Stable equilibrium means if this is the dipole, if pen is the dipole and two opposite forces. Let me pull this end of the pen in this direction, this end of the pen in this direction. Okay. If I pull the pen, no question of rotation, and the pen is stable. That is first case. So let me write, if theta is 0 degree, then dipole is said to be in stable equilibrium. This is required for 1 mark. If theta is 180, it is called unstable equilibrium. What is the meaning of unstable equilibrium means? If this is the pen, let me apply force on one end in this direction like this, and this force in this direction. So as long as theta is exactly 180, resultant force is 0, torque is also 0. If it is slightly disturbed, then this scenario will change like this. See, these two forces are on the same line, means in this direction, it will be in equilibrium, but it is highly unstable. If slightly changes means all of a sudden there will be rotation. For that reason, it is said to be unstable equilibrium. If an electric dipole is in a uniform electric field like this, then net force is 0 because they are equal and opposite forces, but net torque is non-zero, means there is turning tendency. If an electric dipole is in a non-uniform electric field, these are uniform. If it is non-uniform electric field, then both are non-zero. Net force is non-zero, net torque is also non-zero. Means there will be resultant acceleration because of net force and there is rotational motion. This is with respect to non-uniform electric field. Probable questions from this topic. Probable question from this topic. Mention an expression for torque on an electric dipole in an external electric field. Explain the terms. This can be asked for 1 mark or 2 marks. You have to explain the terms. Expression for torque, P cross E or Pe sin theta into n cap. Okay. What is the direction of torque on an electric dipole in an external electric field? Direction of torque is perpendicular to plane containing both P and E, following right hand screw rule. Mention the direction. 1 mark. What is the torque on an electric dipole when angle between dipole moment and electric field is 0? There are 3 cases, right? Extreme cases: 0 degree, 180 degree and 90 degree. This is for 1 mark. What is the torque on an electric dipole when angle between dipole moment and electric field is 90 degree and 180 degree, each 1 1. At what angle between dipole moment and electric field the torque is minimum? Minimum means 0. Maximum is Pe. You have to mention the angles. 1 mark or 2 marks. At what angle stable equilibrium between dipole moment and electric field is achieved? At what angle stable equilibrium is achieved? 1 mark. Unstable equilibrium. 1 mark. Just you have to mention the angle. Is the resultant force on an electric dipole 0 when it is placed in an uniform electric field? Uniform electric field means resultant force is 0. Answer is yes. 1 mark. Is the resultant force on an electric dipole 0 when it is placed in a non-uniform electric field? Non-uniform means resultant force is not zero. No. What is the torque on an electric dipole when the dipole axis is parallel to the applied electric field? Parallel to means either theta 0 degree or 180 degree. So torque is 0. Derive an expression for torque on an electric dipole. Of course, electric dipole in an external electric field. It should be there. This can be asked for 3 marks, 4 or 5. Suppose if the question is asked for 5 marks, they will also ask you to discuss with respect to angles 0, 90 and 180. Linear charge density. Name itself says linear charge density means charge by length. There are 3 types. Linear charge density, let us denote that by lambda, equal to charge by length. Okay. So SI unit of charge by length is coulomb per meter. If it is coulomb, then dimensional formula for coulomb is AT, ampere time. Per meter means L minus 1. AT L minus 1 is lambda. Linear charge density is used whenever charge is on a line. If this is a conductor with charge on the conductor, something like this, then total charge by total length is lambda. If the charge density is uniform, distribution of charge is uniform, then lambda, which is total charge by total length, can also be written as small charge dq by dl or delta q by delta L. Delta means any difference, dq means very small difference. Okay. Now, if it is linear charge density, then electric field is given by, because of this conductor with charge, electric field is given by 1 by 4 pi epsilon naught. So in place of charge, we can write lambda into dl, lambda into delta L, lambda into dl or lambda into delta L divided by r square, because you know electric field is given by constant q by r square. This is for q, this is r square. And for total charge, we need to integrate. Integration of 1 by 4 pi epsilon naught lambda delta L by r square. Okay. This gives total electric field. Similarly, we define one more quantity called surface charge density. Surface charge density usually denoted by sigma, and sigma equal to charge by area, or else small charge by small area, or else delta q by delta L, delta q by delta A. dq means very small charge, delta q means any number, q means total charge. If this is a sheet of charge, then total charge by total area gives sigma. All small charge in this region divided by this area gives sigma. This equal to this equal to this only when charge density is constant. If charge density is not uniform, then it is appropriate to use dq by dA. If charge density is uniform, q by A. Okay. Now, because of this charge, what is the electric field at point P? First, because of this charge distribution, what is the electric field means? dE equal to 1 by 4 pi epsilon naught Denominator should be r square. In place of charge, you can write sigma into dA, or else if it is delta Q, sigma into delta A. So it is sigma into delta A. Because of this charge, electric field at P is given by this equation. Because of total charge, what is the electric field means? We have to integrate this equation, sigma into delta A by r square. This is 1 by 4 pi epsilon naught. There is similarity. Very easily you can write. After surface charge, we read about linear, line, area, surface charge. Now volume. Volume charge density. Okay. Volume charge density is represented by rho. In 11th standard, we have used this for density. Now let us use this for volume charge density. Volume charge density is charge by volume, or very small charge in very small volume dV, or else some charge dQ in some volume dV. Here SI unit is coulomb per meter cube. Okay. Now let this be some arrangement, three-dimensional. Let me write 3D, and this has charge. You consider small region. This is small area on the surface. This is small region, volume. Okay. Because of this volume, charge, electric field at point P is given by, this is dE, 1 by 4 pi epsilon naught into charge is delta Q by r square. So in place of delta Q, I can write rho into delta V. Rho into delta V. Wait for some time. Let me finish this and we can write neatly. Okay. And total electric field means, because of the entire charge, what is the electric field at point P means, we have to integrate this 1 by 4 pi epsilon naught into rho delta V by r square. So this is how electric field can be found out for distribution of charge. Volume distribution means throughout the material there should be charge. Surface charge density means charge should be only on the surface. Linear charge density. It is the ratio of total charge to total length of the charge body. Let me denote this by lambda equal to charge by length. It is Q by L. SI unit is coulomb per meter. Dimensional formula is coulomb is A T. Again, A is ampere, T is time. Meter is length, L, power minus 1, minus 1. Now second, surface charge density. Surface charge density denoted by sigma. Just like this, it is the ratio of total charge to total area of the charge body. Instead of length, we have to write area, isn't it? It is the ratio of total charge to total area of the charge body. Therefore, sigma equal to charge by area. It is Q by A. Coulomb per meter square. Again, coulomb is A T. This A is area. This is ampere time. Okay. Meter square. Meter is unit of length. Length power minus 2. Next is volume charge density. Next is volume charge density. Volume charge density denoted by rho. It is the ratio of total charge to total length. Surface is total charge to total area. This should be total charge to total volume. It is the ratio of total charge to total volume of the charge body. Rho equal to charge by volume, Q by capital V. So SI unit is coulomb per meter cube. If it is mass density, it is mass by volume. It is charge density, charge by volume. Coulomb, ampere time, meter cube, L minus 3. This is the dimensional formula. Now, electric field at a point due to linear charge distribution. Understand the diagram. This is a conductor and it is charged. After completing the diagram, let me write remaining charges. For time being, these two. Okay. This is a charged wire. This is point P. We have to find electric field at point P. For that, let us consider small region of this conductor. That small region is called charge element. Charge element. Small region of the conductor. And that is also charged. Let this be small region of the conductor. Charge element. Okay. Because of this charge, plus charge, this small region is also positively charged. So distance of P from this charge element. Distance of P from the charge element. So this is the position vector of P from this charge element. Let me denote it by R dash. This is vector, position vector. This is some arbitrary origin, O, reference point. So position of this charge element from O. This is one more position vector. Understand? With respect to this origin, this is the position of charge element. So that position vector is R. With respect to charge element, P is represented by this position vector. If you can see, these two vectors are in order. So what is the resultant vector means? Resultant from the origin means closing side of the triangle taken in the reverse order. So this is closing side taken in the reverse order. So let us denote this by delta R. This is also position vector of P with respect to this origin. But what we want is electric field due to linear charge distribution. Electric field at P due to this element means only this distance matters. Okay. So that electric field is dE equal to 1 by 4 pi epsilon naught. If the conductor is positively charged, then electric field is in the direction of R dash. This length is delta L. Charge density is lambda. Therefore, in place of delta Q, I can write lambda into delta L, where delta is length of this, divided by distance square. Distance between these two is R dash. R dash square. This is not R to the power of 12, it is R dash square. To understand, right bracket, into what is the direction of delta E means for positive charge? It is along R dash. So let me write unit vector. If it is positive charge, electric field is in this direction. If it is negative charge, it is towards, electric field is towards. For that case, we have to write minus R dash. So this is electric field at P due to charge element. Now what is due to entire conductor means we have to integrate. So total electric field equal to integration of this 1 by 4 pi epsilon naught lambda delta L by R dash square into R cap. After completion of diagram, let me write few more charges. Okay. Now here, what is delta L? For the sake of clarity, where delta L, length of the charge element, epsilon naught, you know epsilon naught is absolute permittivity of free space. And what is R dash? R dash is distance of P from the charge element, this distance. And what is R dash cap? It is unit vector of the position vector. Again, quickly, R is position of delta L, small length of the conductor with respect to some origin. R dash is position of P with respect to the current element. Delta R is position of P from that origin, reference. Since we want from this element to P, this distance matters. So this position vector matters. Don't worry about these equations. Okay. Only in few places we will be using. Electric field at a point due to a surface charge distribution. In surface charge distribution, we have to consider surface charge density sigma. Okay. Let this be a sheet of charge, positively charged. Okay. This is point P. To find electric field at P due to this entire surface, let us consider small region. Area of the small region is delta A. If total area is charged, then even the small region is also charged. So what is the electric field at P due to this small region means this distance matters. R dash. This is some origin O. What is the position vector of delta A from this origin means now P from O, position vector of P from O. This is delta R. This is R. This is R. R is position vector of delta A from the origin. R dash is position vector of P from delta A. What matters is this distance. So just like previous case, electric field at E due to the small region is dE equal to 1 by 4 pi epsilon naught into total charge. Charge is sigma into delta A. This gives charge in this region divided by R dash square into r dash cap. So what is the electric field due to entire charge means we have to integrate. It is integration of 1 by 4 pi epsilon naught sigma into delta A by r dash square into r dash cap. So sigma appears due to surface charge, where sigma is surface charge density. Students, what is r dash? It is distance of P from the charge delta Q. Distance of P from, call it, charge element. And what is r dash cap? It is unit vector from charge element to P. Charge element to P. This distance matters. Therefore r dash. Electric field at a point due to a volume charge distribution. Volume charge distribution means for a 3D object. Let this be some 3D object, 3-dimensional object, which is charged. Okay. In this small region which is called charge element. Charge on this is delta Q and volume of this is delta V. Now this is point P. We have to find electric field at P due to this element. That is dE equal to 1 by 4 pi epsilon naught into delta Q. In place of delta Q, I can write rho into delta V by distance r dash square. Now you know we have to consider distance from the charge element to point P. This distance is r dash. Vector is just like previous cases. What is the position of this with respect to some origin? So from this point origin to this charge element, this is r. This is the origin. So from the origin to point P means again triangle law, closing side of the triangle. Okay. So this is delta r. For us, this r dash matters. So what is the total electric field means? It is integration of 1 by 4 pi epsilon naught into rho delta V by r dash square. Of course there should be r cap. R dash cap. That time this becomes a vector. Let us write vector symbol. Therefore r dash. R dash is away for a positive charge. If it is negatively charged, then electric field will be towards. Okay. Now after writing everything, we can draw some more charges. What is rho? Rho is volume charge density. And what is r cap? Sorry, r dash. R dash is distance of P from the charge element. What is r dash cap? Unit vector from charge element to P. Charge element to P. So we can write this as the unit vector. R dash cap. These topics, at least you should know answer to all these questions. These are the most probable questions from these topics. Okay. What is linear charge density? Just statement and SI unit. This can be asked for 1 mark or 2 marks. Surface charge density, SI unit, 1 or 2. Volume charge density, SI unit, 1 or 2. If you have idea about the questions, then you can limit your thinking, isn't it? It doesn't look weird, or it doesn't look very clumsy, or it doesn't look very tough topic.